decay.
Hesham Faham, you will talk about long-lived particle searches in heavy ion collisions.
I can start. So good afternoon, everyone. So my name is Hesham Faham. I'm a PhD student at VUB and UC Louvain in Belgium. And today I'll be talking about long-lived particle searches in heavy ion collisions at the LHC. So this talk is split into three main parts. In the first one, I will motivate why we search for long-lived particles in heavy ion collisions. And given the talks that I have just given, I guess that must be very brief, and I'll make sure of that. And then in the second part, I will review a previous study that was done by my collaborators on the search of LLPs in heavy ion collisions. And then in the last part of the talk, I'll try to walk you out of this study into a new study that we're working on that can be seen as a continuation of it. So we start with the first part. So why heavy ion searches at the LHC? As probably most of you know, new physics might not be necessarily heavy, but might also have a very small coupling to the standard model, and that can lead to the production of long-lived particles. And for long-lived particles, the benefits of heavy ion searches can be almost an ideal primary vertexing environment compared to PP collisions or to high luminosity runs in general. If also this new physics is of low masses, then exactly what Susanna was talking about, these minimal triggers in heavy ions can help accessing those low mass signals with soft final states. On the other hand, just for completeness, heavy ion collisions can offer entirely new production mechanisms. This is not something I'll be talking about, but it was covered in several talks during this workshop. So the pileup problem, so as you know, in proton-proton runs, overlapping collisions with punch would translate into pileup, and that leads to high thresholds compared to in PP collisions compared to what can be used in heavy ion runs. And it can also lead to complication in the reconstruction of final states from displaced vertices, as demonstrated in this figure. While on the other hand, in heavy ion collisions, it's usually one true primary interaction as expected. So now moving into the study that was done by my collaborators and on this topic. So they were looking for heavy neutrinos production in displaced vertices. And for that, the standard model is minimally extended with right-handed neutrinos, as you can see in equation 1, in which the right-handed neutrino is coupled to the Higgs doublet of the standard model and the lepton doublet via some Yukawa matrix here. This interaction with the standard model is described by the mixing angle you can see in 2, and then this quantity can be interpreted in relation to the production cross-section of these heavy neutrinos, a quantity that we'll be using later when we're showing the plots and the results. After electroweak symmetry breaking, the Lagrangian reads as a superset of some interaction terms in which n here is the heavy neutrino mass eigenstate. So now we move to the actual search. So it turns out that heavy neutrino masses below the weak gauge bosons, they can lead to displaced vertex signals at the LHC. So this is exactly what I'll be talking about. So there are two production modes that are to be considered in this study. So the production of heavy neutrinos in W boson decays and in B meson decays. So starting with the W boson decays one. So the simulation of this process was done in MADGRAPH, and these event samples that we used were triggered by a singular pair of muons, and a single muon trigger was set to be like 25 GeV, this mu plus that you can see from this diagram here. And also, by the way, these two red dots on the Feynman diagram, they indicate a very tiny coupling of the heavy neutrinos. In this search, backgrounds from long-lived standard model hadrons was suppressed by a minimum displacement requirement of this interesting secondary vertex, and also the B mesons background can be the contamination from the B mesons background can be suppressed by requirement on two displaced tracks to have an invariant mass which is greater than 5 GeV. As you can see from that figure here, that these blue dots, they represent standard model states, and then you can see that a cut above 5 GeV suppresses the contamination from B mesons background. So before going to the production of heavy neutrinos on B mesons decay, I just want to also discussed this simplified detector model that was used in this study to estimate the number of displaced vertex events using this analytical formula here that you can see in equation 4. And this analytic formula, in the case of PP collisions, for instance, and in the W boson case, it can estimate the sensitivity, as you can see in this figure, represented by these three contours corresponding to three different luminosity, integrated luminosity values. And these colored lines here in this sensitivity estimation illustrates the obstacles that can hinder the reach from more improvement, and that is if the displacement is too large, that the heavy neutronous decays out of the detector, or it's too short, or it's too minimal, that it decays promptly. So it turns out that this simplified detector model helped a lot in the B meson decays case, because the simulation of heavy neutrinos in B mesons decays is technically challenging, and thus this simplified detector model was modified accordingly to estimate the sensitivity in heavy ion runs for the B mesons, as you can see in equation 5. More importantly, the figure, you can see, it shows the sensitivity estimate as well, but the temperature map here, it shows the number of events predicted by the simplified detector model to the number of events predicted by the actual simulation, and that was done in the W boson's case to check how well this detector model is working. And as you can see, that it's working really well here, as if you can see from the temperature map. To the results of this analysis. So here we see two plots. On the left-hand side is the results for the W boson case, and on the right-hand side is the results for the B mesons case. The three contour lines, they refer to different runs. So the red one is for lead-lead, the green one is for argon, and the blue one is for the proton-proton. The gray regions are the regions excluded by experiment. And if you can look at, if you see the case of the W bosons, you see that the region of the parameter space that can be probed by PP is larger than the region that can be probed by argon run, for instance. And for the lead case, the region that can be probed is actually excluded by the experiment. So in this search, or this case of the search, like the W boson case, you see that the heavy ions doesn't really compete with pileup, with proton-proton. I started thinking about pileup already, because this is the second part of the talk. For the B mesons case, and exploiting these low trigger thresholds to access low PT physics, you can see that in the argon case, for instance, heavy ion can provide some improvement compared to PP, in which you can't do that because you can't afford going so low in the triggers. It's worth mentioning now, before going to the third part of the talk, that the absence of pileup in heavy ions was not exploited in this study. So now moving to our current work, and in the idea of the current work that we're doing, that is, we want to exploit the low thresholds, as you've just seen in the B mesons case. We also want to include detector simulation with pileup conditions, so we can see whether the absence of pileup can give heavy ions a better handle over PP collisions. So in that case, we look for di-muon soft signatures, so soft and displaced muon tracks, and as you've just seen the previous talk by Susanna, this was motivated in a more detailed way. So for long-lived signatures at the LHC, we use a simplified model for dark matter, and this model predicts some new dark matter states. So this displaced chi2 here, that you can see that it goes to some dark matter state chi1 and to some standard model object X. And on the right-hand side, this diagram shows the actual process that we're looking for. So this standard model object here is represented by these two fermions that decays via some light mediator, and this whole vertex is displaced because the long lifetime of this chi2. We set the so the y0 is set, the y0, sorry, is set at 5 GeV, so fairly light, and then and the our search is based on this Feynman diagram, or with this value of y naught. So a little bit into the simulation of these processes. So the heavy ions signal simulation was done by MADGRAPH, and for that the beam energies has to be modified to consider the nuclear enhancement in the heavy ions case. Also, a dedicated pattern distribution function should be used to consider the heavy ion ones. And the most importantly is not the actual number of the cross sections that we get in the PP and in the heavy ions case, but the fact that the enhancement in the cross section, which is expected because of the modifications of the beam energies here. So we get what I expect, which is 4 orders of magnitude larger cross section in the heavy ions case compared to the PP. And a little bit also into the background. So we use this background process to be bar to mu plus mu minus. And to simulate B physics in Pythia, we use these hard QCD switches. We also modify the beams, center of mass energy, and so on. And we still get from these cross sections for the background, we still get the same order of the same 4 orders of magnitude enhancement as in the signal simulation. So into the actual analysis, as I've mentioned, the analysis runs through Delphis for detector simulation to simulate the pileup, and then the actual analysis that we're doing actually follows what we call the maximum displacement strategy, because we were interested in displaced physics. So we only select in this case, we only select the mu1 pair that has one track that has the largest transverse impact parameter. It's worth mentioning also that in this analysis, we have 2 free parameters. So we have the secondary vertex radius, so that's the distance between the origin of 2 tracks which are displaced, and the minimal transverse impact parameter, which is the minimal tracks displacement which is required. So far, these 2 parameters are free parameters. And so a first look into the output of this analysis. On the left-hand side is the mass of this y naught, this light mediator in the signal case. And the legends here corresponds to different conditions of the run. So the blue one is for no pileup, the red one is for pileup, and the green one is for the heavy ions. And we use this plot on the left-hand side to show how well our vertexing algorithm is working, how well we were able to reconstruct the signal. And as you can see, this plot gives an indication that our vertexing algorithm is working fairly well. On the right-hand side, however, it's a distribution in the background for the transverse impact parameter for one of the 2 tracks that we use to do the reconstruction. And this plot here, from this plot here, we see preliminary indications that a further displacement in the further displacement cut into the right-hand side actually cuts a big portion of the heavy ions background. And we think that might give some enhancement for the sensitivity in the heavy ions over PP. I wish I had more results to show you now, but we're still working on that, and hopefully I'll be updating you with more results soon. So that brings me to my summary. So heavy ions might have a better handle over PP in some corners of the parameter space where the signal is soft and displaced. The study of heavy neutrinos in displaced vertices, it showed some improvement for heavy ions over PP because of the reduced trigger thresholds. And for the dark matter LLP search that we're working on now, progress has been made in the simulation front, and we're currently studying the signal and the background distribution to test our initial hypothesis. We're also considering studying the detector simulation and in particular the pileup in the high luminosity LHC case. Thank you very much for your attention.
Thank you, Hesham. Do we have questions for Hesham? There's one by Susanna, yeah?
Yeah, thanks. Actually, it's about the B meson decays for the light heavy neutral leptons. How did you deal with the heavy flavor background in that case?
So the the heavy, so for the backgrounds,
So this was about the heavy neutral lepton, right? But as far as I know, you also studied the light ones that stem from B meson decays. So there the particles are really soft, right? But like the new B decay looks very much like the standard model decay. So the spectra should come out very similar. And I'm wondering how you suppress the heavy flavor background in that case.
So mainly the background from the long-lived standard model hadrons were suppressed by minimal displacement requirement.
So you basically looked at the long lifetime regime and got rid of them in that way?
Yes.
Okay, thanks.
Marco?
Yeah, I was just about to comment what Hesham already said, because there Hesham was kind of presenting our earlier work, but Hesham, you answered the question very accurately already. So
very good.
I have nothing more to add.
Very good.
Okay, further questions?